So to find the zeros of any function, you set the function value equal to 0 and then solve for the values of x where that is true. So in this case, f of x we're going to set equal to 0. And what this will also do is give you the y-intercepts of the equation. So what we have is a quadratic equation. So it's going to look something like this, or it's going to look something like this. And it may cross the x-axis. You can have quadratic equations that don't cross the x-axis. And under those circumstances, you have no real roots. But in this case, we do have real roots. So first thing I'm going to do is I'm going to just put the function on the left-hand side. And then we just need to factor. So the first terms, as far as x, one has to be 2 and one has to be 1. 2 times 1 is 2. And then the question is, we have to have the second number be a product of two numbers that's 30. So they could be 5 and 6. They could be 3 and 10. They could be 2 and 15. They could be 1 and 30. Most likely, it's going to be either one of these two, I would think. So let's just think about it. Let's just put it in here and see what happens. So let's say this is 5 and this is 6. So you'd have 2 times 6 is 12, and then we'd have 5 times 1, which is 5. 12 minus 5 is 7. So that looks like the right choice. And then we have to decide which one's going to be positive or negative. Well, the middle term is negative, so we want the product that gives us the negative value to be the larger one. So 2 times 6 is 12, which is larger than 5 times 1. So we're going to put the negative sign here and put the positive sign there. So let's just double check it. 2x times x is 2x squared. We'll get negative 12x plus 5x, which is negative 7x, and 5 times negative 6 is 30. Okay, so there we have done it. And for the left side to be equal to 0, either one of these factors can be 0. So we set that equal to 0. We subtract 5 from both sides. We divide by 2. So one of these zeros is 5/2, and the other one is x equals 6. So those are my two zeros, which are also my x-intercepts. And I was going to plot it. So let me open my graphing program here. I'll just make it big so you can see it. So our function is 2x squared minus 7x minus 30. And we graph it. And I'm going to zoom out a little bit. So you see we have an x-intercept of negative 2.5, which is 5/2, and we have an x-intercept positive 6. So that shows that we did it right. Okay, the next one. So when you have a rational function, all you have to do is have the numerator go to 0 to get the zeros. So we don't have to worry about the denominator as far as the zeros. We have to worry about it in terms of vertical asymptotes. So what we do is we would take the numerator, not the entire function, but just the numerator, and set that equal to 0. And again, I'm going to switch the two sides, and then we'll factor it. So what two numbers multiply together give me 14? Well, 1 and 14 are 2 and 7. And 2 plus 7 is 9, so that looks like a good choice. 7, 2. And they're going to be the same sign because this 14 is positive. So they can be both negative or both positive. And because the middle term here is negative, that means they need to be negative. And again, you can check it. X times x is x squared. Negative 7x plus negative 2x is negative 9x. Again, for this left-hand side to be 0, either one of the factors can be 0. So we get x-intercepts of 2 and 7. And again, I'll graph that. So we'll graph the entire function. So we have x, put them in parentheses, x squared minus 9x plus 14 divided by 4x. And we'll graph it. And, you know, right now it's not completely obvious where it intersects the x-axis. So what you can do is you could zoom in the y direction, and that accentuates the curvature. And you see we've got an x-intercept at 2 and one at x equals 7. So that's correct. Let's just go back to this just to show you what this function. So it's kind of like a reciprocal function in that it goes to positive infinity at 0 and goes to negative infinity at 0, depending upon which direction you're coming from. It does have a slant asymptote, and as it said, it has 2 x-intercepts. Okay, number 19. So if you have a polynomial where the constant term does not exist, so I don't have like plus 5 or minus 10, the first thing you want to do is you can factor out x. So you'll get x times, actually you could factor out a half x. And what that would leave is x squared minus 2x, x squared minus 2. The reason I did that is so that the coefficient in front of x squared would be 1. And so a half, to get the expression in the parentheses, you take the number you're factoring out and divide each term by that factor. So I'm factoring out a half, so I divide a half by a half, which leaves 1. And here's my coefficient is negative 1, so negative 1 divided by a half is a negative 2. So just like the previous problem, we set, well, actually the first problem, we set the value of the function equal to 0 and say what values of x is that true. So we have actually 3 solutions because we really have 1/2 times x minus 0 times x squared minus 2. I put the 0 in there so it looks just like all these other ones. You can also think that if x is 0, then this whole thing is going to be 0 because you'll have a half times 0 times some number. So one solution is when x minus 0 equals 0, or when x equals 0. And the other solutions are when x squared minus 2 equals 0. And the reason I'm not factoring this is because there's no linear term, and so you can solve this without factoring it. So I'd add 2 to both sides, and you take the square root, so you get x is plus or minus the square root of 2. So we have three zeros. X equals 0, x equals negative the square root of 2, and x equals positive the square root of 2. So let's look at this one. Let's go to standard zoom. So the function is 1/2 times x cubed minus x. And there it is. It's a third order equation. And we have 1, 2, 3 x-intercepts. One is at 0. The other one is at 1.431. And if you take the square root of 2, you'll find out it's 1.4 something. And then here's a positive square root of 2. Okay, number 23. So one thing is all these other ones have had a domain of all real numbers except this one where x cannot equal 0. Here x has to be 2x has to be greater than or equal to 0. So the argument of the trig of the square root is greater than 0. So you'll get x is greater than 0. So our zeros are only going to be at values of x greater than 0. So we do the same thing. We say, okay, 0 is the value of the function is equal to the square root of 2x minus 1. We'll move them to the left-hand side. Let's add 1 to both sides. And then we'll square both sides. So 2x, square root of 2x squared is just 2x. And on the right-hand side, we get 1 squared, which is 1. And then, so we get 2x equals 1, or x equals a half, which is in the domain. So that is the x-intercept. So let's go check it out. Square root of 2x minus 1. So the function square root of 2x minus 1. I'm going to graph it, and there it is. And we can see that the x-intercept's at 1/2. The domain is all positive real numbers. Okay, it says use a graphing utility, find the zeros and verify. So let's just verify because we've already, let's verify doing it analytically. So again, we set the numerator equal to 0 for rational functions. And then we add 1 to both sides, and we divide by 3, and so we get x is 1/3 is the x-intercept, one x-intercept. There's a vertical asymptote at x equals 6. The domain is all real numbers except x equals 6. So we'll go to graphing utility. So it's the quantity 3x minus 1 divided by 3x minus 1 divided by the quantity x minus 6. You got to put those parentheses in there. And there we go. And actually, let's just zoom out a little bit. There's more of the function. So you can see that it's kind of has a reciprocal behavior around the x, the vertical asymptote, which was at x equals 6. But the x-intercept is right there, which says it's equal to 1/3, which is what we got. Okay. 29. Use graphing utility to estimate the relative minimum and maximum. So I'm going to get my graph. So we're just going to plot it. So let's go to the graphing program and do x minus 4 times x minus something 2. And we say graph. So there it is. It's a polynomial if you multiply it out. And you can see we have an x-intercept of 2 and an x-intercept of 4. And oh, that's the okay, I'm not asking for that. They're asking for the relative minimums and maximums. Well, it's a polynomial, so you only have one. You either have a relative minimum or a relative maximum. If the coefficient, the sign in front of x squared is positive, then it looks this way, pointing upward. And if it was negative x squared, then it would be pointing downward. So since it's positive x squared, it's pointing upward. And the value of x where you have relative minimum right here is x equals 3, and the value is y equals -1. Now you have to wait to do calculus to be able to figure out analytically what that is. So the answer here is it's a relative minimum, and it is at x equals 3, y equals -1. And then our final problem is this third order polynomial. So let's plot that. That's number 52. So we'll go to here. So 52 is x cubed minus 3x squared minus x plus 1. So we graph it, and there it is. I'm going to zoom out just a little bit in the y direction. So this is what we call a relative maximum, because around this point, this value of x, it's more negative or smaller. I guess more towards the negative side. So this is relative maximum. This is a relative minimum. So the relative minimum is going to be at y equals, or x equals -0.157, and y equals approximately 1. And the relative minimum is at x equals 2.186, y equals -5.1. So so that's negative, it's about a -1/6, maybe a 1/7. So we'll just say -0.14 and +1.1. So that was the relative max was -0.14 something and 1.1, and the relative minimum, let's go back again, make sure I did that one right, 0.14 something, and this one's about 2.2 -5.1, 2.2 -5.1. Now they don't ask us to do this, and we'll do this later. The question is, how do you find the zeros of this? That doesn't help us find the maximums and minimums necessarily, but I'm just going to do this. And you can actually, let's just go back to the drawing just to show graphically. You can see there's a 0. Well, there's not a 0 that's on a nice value of x, so it would be hard to do that using long division. So we'll just keep it the way it is. And I think that's it.